of Gauss law. So the very first application we have seen the identification or determination of electric field, determination of electric field, okay, due to the infinite line charge, electric field, that is determination of electric field due to infinite line charge, okay, and also we have seen infinite sheet of charge, so infinite sheet of charge and spherical shell of charge, spherical shell of charge. This is what we have seen in the last class. So just we should recall. So what is that we have seen so far? Okay. So this is what we have discussed. Okay. Yes. So this is the infinite line charge. So without using the integration much, without using in the integral calculus much, so we have been able to find out what exactly is the electric field due to infinite line charge. So what is that we have done? We have assumed a Gaussian surface. We have assumed a Gaussian surface, that is a closed surface. So which is nothing but right circular cylindrical surface of radius r. I am interested in finding the electric field at this point. So for that reason, I have assumed a Gaussian surface. That Gaussian surface, it is nothing but a right circular cylindrical surface having radius r and length L. Okay, and for all Gaussian surface, it has to be a closed one. Therefore, we also assume that both the ends of the cylinder are closed at this point. Okay, so what is the discussion we have made here? So there are three surfaces. Okay, there are three surfaces. So one is the surface, that is a top surface and the bottom surface, and other one is a closed surface. So the flux can emanate. The flux can emanate in on three surfaces. So one at the bottom and one at the top and one at the that is the closed the curved surface. Okay. So and what we have discussed, that means the flux lines will be perpendicular. Flux lines will be what? Perpendicular to the line charge. That is radially, it is moving radially outwards. So there will be no charges or there will be no flux lines. So emanating from the top and the bottom surface, because it is the flux lines will be what parallel to the infinite line charge. There will be no flux lines parallel to the infinite line charge as per our discussion. So there will be no fluxes crossing the areas at the top as well as the bottom. So we will have to find out the total flux, that is d phi, which is on the curved surface only. Okay, that is d phi on the closed surface only. So that is nothing but is a closed surface, that is curved surface only. So if you take out over a complete Gaussian surface, that will be nothing but the total that is a d vector into what the ds vector. So if you just do it, so d is a constant, so you'll be getting like this ds. Okay, so the expression now, so E is equal to what, d by epsilon naught. So you'll be able to solve for E. So using the line charge density, that is nothing but rho L by 2 pi epsilon naught R into AR cap. This is the expression what we have done. And this is nothing but the total flux which is emanating radially outside the Gaussian cylinder. So what we have made use here, we have not used any integrations here. We have just used the concept of linear charge density, and we have solved the or obtained the solution for the total electric field intensity. Okay. Next, what is that we have got? So we have got the infinite sheet of charge. So again, what we have done, we have assumed a cylinder, assumed a cylinder here. So right circular cylindrical surface with both ends closed, and I am interested in finding electric field intensity at P. That P is at a distance of R from the sheet of charge, and this is a planar symmetry. So it is a planar symmetry, or you can call it as, that means the cylinder is assumed to be present on the other side of the sheet also. There are two cylinders, so which is symmetrical in nature, and it is present on either side of the sheet of charge. That is the assumption here. So you have to assume again a cylinder as the Gaussian surface, and where exactly the flux lines crosses, and where exactly the flux lines do not cross. The flux lines will be radially perpendicular. That means the flux lines will be perpendicular to the sheet of charge. That means the flux lines will be like this. The flux lines will be like this. As a result, the flux lines will either cross this side surface or this surface on the left hand side, the right hand side as well as on the right hand side. So there will be no charges or flux lines crossing the curved surface. You will not be having any flux lines crossing the surface that is curved one, because we know that the field will be directly perpendicular to the sheet of charge. So obviously, again, there will be three surfaces you have to take. So one on the one on the side, on one on the curved surface. So you can find the total flux. So the total flux will be equal to phi is equal to phi 1 plus phi 2, that is psi 1 plus psi 2 plus psi 3. So you'll not be having the flux on the curved surface, let there be phi 3. So this will be what, phi 1, the psi 1, and this is be nothing but psi 2. So on the surface which is perpendicular, that means the field lines are perpendicular to the what, the sheet of charge. So the area of those surface will be dA plus dA, that is nothing but 2 times into dA. So the flux lines is equal to what, 2 times of dA. So if you substitute in the expression, so you'll be getting a rho s by 2 epsilon naught. This is the electric field intensity due to sheet of charge. Okay. So if it is clear for you, you can type 0 on the chat box. I'll move on. This is what we have derived. I'm discussing what is that we have derived so far. Yes. So now we shall move on. Next concept what we have derived is obtaining field intensity as a spherical shell of charge. Spherical shell of charge. So what is that we have to find out here? We have to find out E at 3 different points. First point on the shell, second point inside the shell, third point will be outside the shell. These are 3 points you have to, where you have to find the electric field intensity. So the first what is on the screen is outside the shell. outside the shell. The point P is outside the shell. This is the shell of radius R, and I'm taking a point P here. I'm considering a Gaussian surface. That Gaussian surface is also a sphere around it. So Gaussian sphere you can call it as. So and the radial means the field will be radially outwards. Okay, and if you just solve for it, so you'll be getting as E as q by 4 pi epsilon naught r square into a r cap. Okay, and the field is equal along the radial lines. The field at a point will be equal along the radial lines. This is due to what the Gauss law. Okay, it's now field at a point on the shell. This is what on the shell. So again, the radius of the shell is r. Same equation holds good here, but you have to choose the radial distance as capital R here. So it is q by 4 pi epsilon naught r square into r cap. So here it was small letter r because that is a r is the distance from the origin, radial distance from the origin. So what is that I have taken here? Next, this is on the shell here. Next, what might happen here? So it is inside the shell. So inside the shell, this is the charged shell. So we are assuming that the charges are on the shell, okay, on the outer surface of the shell. And I'm having a point P at this point, which is inside the shell. So I am interested in finding E at this point. Okay. So as a result, we know that there cannot be any charges inside the charged shell because charged shell cannot house any of the charges. So the charge inside the um, charged shell, it is nothing but 0. So you will not be having any field inside the uh, charged shell, okay, spherical shell. So this is what we have discussed for the spherical shell, and this is the variation of E for a spherical shell. Okay, so for until R is equal to R, so you will be having the field as 0. You'll be having the field as 0 because you'll not be having any field where the distance is lesser than the radius of the shell. Okay, I repeat, you'll not be having any field at a point which is less than the radius of the actual shell. So at the point where the radius of the shell is equal to the distance at the point where you are measuring the field equals the field maximum. Field will be maximum. That is, the field will be maximum on the shell. The field will be maximum on the shell, and it decreases. And it decreases when the distance from the origin increases. That means R increases. This is a variation of E for a spherical shell. Okay, this is what we have discussed so far. So I'll just write all the three equations together. So E is equal to 0 and E is equal to, that is R is less than R. So and E is equal to Q by 4 pi epsilon naught R square AR cap, that is R is equal to R, and Q by 4 pi epsilon naught R square, that is R square AR cap, where R is greater than R. Okay, this is 1, 2, and 3. Okay, this is the region 1, and this is region 2, and this is region 3. Okay, so when it is on the shell, the point is on the shell, so charged shell, so the field will be maximum. Okay, yes. So this is what we have discussed so far. Yes. Now, coming back to the one more example here. So what is happening now? So we have got a charged sphere. So until now we have seen the charged shell, which can be an hollow one. So now it is charged sphere. Okay, charged sphere, that is solid sphere. So what we are taking is talking about is now charged sphere. So this is the charged sphere what we are discussing, and the dotted portion is the uniformly distributed charges. Uniformly distributed charges. Okay, so that we can see like this. That is rho v is the volume charge density of the sphere. Rho v is what? Volume charge density. Okay, so the solid sphere of solid sphere. So it is given. Now again we have to find out the electric field due to this charge sphere at different points. First point can be outside the sphere, on the sphere, and inside the sphere, inside the sphere. So just don't get confused with the spherical shell and the charged sphere. On the spherical shell, that means over the surface the charges were accumulated. Here, charged sphere means charges are inside the sphere. Charges are inside the sphere. Okay. So now, to find electric field intensity, we make use of Gauss law. Um, how do we solve using Gauss law? We find the electric flux density. Okay, and that to find electric flux density, you require the charges. That is what exactly the charge which is flowing through a given surface, or the flux flowing through a given surface. So the flux is nothing but the charge inside the sphere. So we have to assume now again a Gaussian surface at each and every region, and then we can solve it. First case is like this. So the point is outside the sphere at a distance of r, small letter r. So this is my point here. Follow me on the screen. This is my point here, and this is at a distance of r from the center of the sphere. Okay, so the flux lines are diverging radially outwards, and thus it will be normal to the Gaussian surface, and it will be what? Normal to the Gaussian surface. So if you take out an elementary surface like this ds, so your d psi is equal to d vector into ds vector. This is the fundamentals. So that is equal to d vector. I can write as it will be perpendicular to the surface area, that is radially outwards. So that means d into ar cap, and that is multiplied by or dot product by. So this is one for this one d vector, another one for ds vector. So this is ds into n cap. So n cap is the per normal vector that is perpendicular to the small surface. Okay. Yes, ar cap into n cap is equal to 1, because they are the unit vectors, and which are parallel to each other. So obviously we'll be getting d into ds. Okay, so the ds, what is the ds? Ds is what? The small area. the small area. So, or small area which is considered here. So I want to find now the total flux. That is psi is equal to integration of small flux. So it is nothing but d into ds. Hello. Yes. Next, d is constant over the surface. So obviously integral of ds. So what is the area of the sphere Gaussian surface? What is the area of the Gaussian surface? Any idea? What is the area of the Gaussian surface? That is sphere.
4 by 3 pi r cube.
4 pi
Gaussian
r square.
4 pi r square. It is 4 pi r square into d. This is the total flux like this. So your total flux psi is equal to d into 4 pi r square. That is equal to total flux housed by the sphere. Okay. So now d is equal to q by 4 pi r square. Okay. And now I want E vector. That is E vector is equal to d by epsilon naught r square into ar cap. So this is the expression for field at a point outside the sphere. At a point outside the sphere. Okay. Yes. So very simple. Without any integrations, we have done it. A double integral or triple integral, we have not used it. Next. So what is this? Can anybody guess it here?
On the spheres.
Yeah, point is on the charged sphere. So this is a uniformly charged sphere. So we are required to find the field at point P, which is on the sphere. So what we can do, we can use the same principles here. So total flux is equal to integration of all the flux across a given surface, and that is equal to d into ds. And what exactly ds now? So ds is nothing but 4 into pi into r square, because this is the radius of the sphere to be considered. That is Gaussian surface, which is limited to this point, to the point P. Okay, that is equal to psi, and that is nothing but equal to flux. Therefore, your d is equal to q by 4 pi r square. As a result, your E vector is equal to q by 4 pi epsilon r square ar cap. Okay, just check out here. This is r here. That is the radius of the exact sphere. And in the previous case, it is nothing but radius of the Gaussian surface. Here, the radius of the Gaussian surface is greater than the radius of the sphere. So here r is greater than r here. And in this case, r is equal to r. That is, Gaussian surface is same as your sphere. Okay. Yes. So now we can take out the next case. Yes. So what is happening here? What is happening here? The point P is inside the charged sphere. So r happens to be your radius of the actual sphere, and this point P is taken to be inside the sphere, which is housing the uniformly distributed charges. The point P is at a radial distance of r. The point P is at a radial distance of r. Okay. So now the sphere is enclosing some charges, and point P is inside the sphere. So what is that we have to conclude now? So the phi is equal to integral of d phi d psi, that is nothing but d into ds. So that is nothing but d into now small surface. So which surface I need to consider now? That small surface ds, and the Gaussian surface. What is the radius of the Gaussian surface, or radius of the sphere? That is Gaussian surface. It is small r. So it is 4 pi r square. Okay. So just follow me here. This is the Gaussian. The dotted line is the Gaussian sphere I am considering, and whose radius is r, which is nothing but the point distance of the point P from the origin. Okay. So this is phi, and that is equal to q. Okay. So what I can find now, so this is the total q is different from the q is enclosed in the Gaussian sphere. There are two q's now. One is the total q, which is enclosed by the actual sphere of radius r, and there is one more q, which is nothing but enclosed by the smaller sphere, that is Gaussian sphere. That is Gaussian dash is the imaginary sphere enclosed by what? The imaginary sphere, that is Gaussian sphere. It is given by d4 pi r square. Okay. So this is what we have taken to be, and this 5, this 5 and this q dash, okay, so which are equal. So how do you find out the q dash in terms of the volume of the okay, into the surface area, that is nothing but volume, that is dv, rho v into what? Dv. So rho v is the volume density, volume charge density. Dv is the volume of the sphere, volume of the sphere of the Gaussian sphere. I'm talking about Gaussian sphere. So it is nothing but 4 by 3 pi r cube. So your q dash is equal to what? Rho v into 4 by 3 pi r cube. So this is the actual formula. So that is to calculate any charge. So rho v is equal to dq by dv. So rho v into dv. So dv is the differential volume. The differential volume of the Gaussian sphere is 4 by 3 pi r cube. And now use this one. So d is equal to, it is q dash by 4 pi r square, and E vector is equal to D vector by epsilon naught. And if you use these two expressions, if you use these two expressions, you will get an simplified expression, that is E vector is equal to D vector by epsilon naught. So D vector, we got to know it as q dash by 4 pi r square. Q dash we know, q dash is rho v into 4 by 3 pi r cube, that divided by 4 pi r square. If you simplify, you will get 1 by 3 times epsilon naught into r into rho v, okay, into a r cap. This is the E vector. I repeat here, E vector is equal to 1 by 3 times epsilon naught into r into rho v into a r cap volts per meter. So this is what the electric field intensity inside the sphere, inside the sphere. So any doubts here?
No doubt, sir.
Yes. So this is the charged sphere I'm talking about. Now, this is the variation. This is the variation of E of a uniformly charged sphere. Okay. So R is equal to R. That is uh, the field intensity decreases as and when it progresses outside the sphere. As and when it progresses outside the sphere, and the field intensity is what linearly increasing from r is equal to 0 to r is equal to r. The field intensity increases from r is equal to 0 to r is equal to r, and it reaches to the maximum value that's supposed to be the point on the sphere and decreases from there onwards. Very simple. So you just have to understand this concept here. Clear? Yes. So this is the region inside the. This is outside the sphere, and this is on the sphere, and this is inside the sphere. Okay. Yes. Don't get confused with a spherical shell and a charged sphere. Okay. So spherical shell means on the surface of the shell you'll be having the charges, whereas on this is charged sphere, inside the sphere will be having charges. Okay. Yes. Next one. So if it is clear for you, please type 0 on the chat box. Yes. So now what is that we have studied so far? We have so far studied finding E. Okay. Finding E for the charged spherical shell. Charged spherical shell, and finding E for charged sphere. For charged sphere. Okay. So this is what we have studied now. So you can get a theory question on this one. You can expect a theory question on this one, or you can expect a problem on this one. Problem on this one. Given the radiuses at different points, and you will be able to solve for the field. That's all. So if you have understood the concept, then it is very simple to solve the problem. Okay. Yes. Now let me take one more application of Gauss law in finding electric field intensity due to the coaxial cable. Coaxial cable, or is called as coaxial cylindrical conductors. Cylindrical conductors. Okay. Yes. This is what coaxial cable we're talking about. Yeah. So there are two cylinders here. One is the solid cylindrical conductor that is inside. Okay, that is a solid cylindrical conductors. That is a one cylinder, and the other one is hollow cylindrical conductor. Hollow cylindrical conductor. So these two are coaxial. These two are coaxial. That means the axis of both the cylinders are same. Also, the length of the conductor is L. Both cylinders having the length as L. Okay. The radius of the solid cylinder is R1. Okay. Then radius of the hollow cylinder, that is outer cylinder, is R2, and its thickness is negligible. Okay. So this is what we have got now. So there are two cylinders. So one is a hollow cylinder which is housing one solid cylinder. So this is the solid cylinder I'm talking about. Solid cylinder whose radius is R1, and this is a hollow cylinder whose radius is R2, which is housing the solid cylinder. Okay. Yes. So it is assumed that there are positive charges uniformly distributed over the outer surface of the inner cylinder. So it is assumption. So basically, this is assumption. So it is assumed that there are positive charges which is uniformly distributed on the surface of the inner cylinder. I repeat, there are uniformly distributed positive charges on the surface of the inner cylinder. Okay, so this is what the assumption here. So the electric field intensity, now what happens, because of the cylindrical symmetry, the intensity remains same all over the surface, that is parallel to the axis. Okay, that is parallel to the axis. So for example, at this point you'll be having same field, at point B you'll be having same field, at point C you'll be having same field, point D you'll be having same field. For example, here A dash you'll be having same field, B dash you'll be having same field, C dash you'll be having same field, like this. So it is radially outwards. The electric field are what, radially outwards, and it will be same. The field intensity will be same. Okay, so that is parallel to the axis. Okay, so now we can identify three regions here. So which are the regions? Can you let me know? Can somebody let me know? There can be three regions here. Yes.
So
Top,
region
bottom,
within the,
bottom.
One by one. Yes. Chandramohan.
so within the cylinder one.
Within the cylinder, inside the cylinder or outer cylinder?
So inside cylinder.
Yes. You
Then
can consider a region. So which is inside the cylinder. Okay, that means I can write that a point here, which is R, is less than R1. Am I right here? Got it? Yes. R is less than R1 means the points will be lesser than the radius of the inner cylinder. Yes. Next point. Next one.
so outer cylinder.
Yes, greater than the outer cylinder. The points can be what, greater than the radius of the outer cylinder. That means outside the hollow cylinder whose radius is R2. Next, one more region you can define.
So between two cylinders.
Exactly, between two cylinders. That means your R can be greater than R1 and less than R2. Okay, so this is what the different regions, what you can uh, define for this coaxial cable. Okay, yes. So just observe this one. So we have got three regions here. So it is R1 and R2, and that R can be anything which can be less than the inner cylinder, radius of the inner cylinder, and it can be more than the radius of the outer cylinder, or it can be between the inner cylinder as well as the outer cylinder. Okay. Yes. Any doubts here? So if this is clear, I can move on. Otherwise, it will be difficult for me to uh, make you understand. Yes. If it is clear for you, please type 0 on the chat box. Yes. Now, let me go further now. So let me consider the first case. Can somebody identify which case it is by looking at the figure? There is a Gaussian surface and which case it is? Or where is the point?
R is greater than R1.
R is greater than R1 and
Less than R2.
R is
Less
less
than
than
R2.
R1.
yes, that means the point is between the two cylinders. Okay, that means it is outside the solid cylinder, that is inner cylinder, and it is inside the hollow cylinder. So this is the case where your Gaussian surface is okay outside the inner cylinder and inside the outer cylinder. That is R is greater than R and less than R2. So now I want to find the field intensity at this point P now. I want to find field intensity at this point P. For that reason, I have assumed a surface, that is Gaussian surface, which is similar to a cylinder, which is similar to another cylinder, okay, whose radius is R. Okay, that is what we have to assume. So this is a Gaussian surface, and it has to be an hollow surface. It has to be a hollow surface, and it is a closed at both the ends. It's closed at both the ends. Okay, and it's also closed at both the ends, and it is coaxial to the other two cylinders. So how much flux can pass through? Where the flux can pass through now? Through this Gaussian surface? That's the next question. The flux can pass through three different regions. That means one from the top surface, and other from the bottom surface, and other from the curved surface. Okay, these are three surfaces available for me in the Gaussian surface, where the flux can pass through, where the flux cannot pass through. That's the next question. Any idea? Where the flux can pass through and where the flux cannot pass through? Yes. Yes, where the flux can pass through and where the flux cannot pass through. There are three surfaces of the Gaussian surface. Gaussian surface, top surface, bottom surface, and curved surface.
Flux can pass through top surface and bottom surface.
No,
The
again,
flux passes through the curved surface.
exactly. Why? Because the density of the flux will be radially outwards. Am I right here? Am I right here? So if you take the flux distribution like this on the inside surface, so these are my positive charges, correct? And there will be some flux density will be in the direction like this. Okay, got it? Due to this flux distribution, due to this flux distribution, due to this flux distribution, the density, flux density will be direct in the direction or will be radially outward. Will be what? Radially outward. Got it? So you will be having flux lines crossing through the um, curved surface, crossing through the curved surface. Okay, so this is what happening in this case. So which will be crossing through this curved surface like this, like this, like this. And here the flux lines will not be crossing through the curved surface. Why? Because the d vector and the angle between the S vector becomes 90 degree. So the dot product of the D component as well as the area component will be equal to 0. Therefore, you will not be having any fluxes or field along the top surface and the bottom surface. Got it? So the angle between them is what? 90. So cos 90 is what? 0. So there will be no flux lines which is along the surface which is perpendicular to um, the surface. There is nothing but this point, these charges. That means the field lines will be emanating radially outwards. Got it? So you'll not be having fluxes on the bottom surface and the flux surface. You'll be having fluxes along the curved surface only. The curved surface area is ds. So the ds is the area along the curved surface. So if you integrate the curved surface, that is nothing but the area of the surface, that is 2 pi r into L, that is the length of the cylinder. So 2 pi r into L is the total curved surface area. So you'll be having flux lines crossing through the curved surface only. Okay. So that is the discussion what we have to do here. Okay. So let me write the flux, total flux. So phi is equal to phi 1, that is phi top, plus phi bottom, plus phi surface. That is nothing but this is 0, and this is nothing but on the surface. So this is, I will write like this, psi. Okay. Yes. So this is psi surface is equal to what? D1 or D vector into what? ds vector and the integral. So d is constant here. So d vector is constant here. So d is constant here. So it is ds vector. So it is nothing but ds. So it is d into 2 pi rl. So this is 2 pi rl is your radius of the sphere, that is Gaussian surface cylinder. Okay, and L is the length of the Gaussian surface, which is cylinder. Okay, this is equal to what? The charge is enclosed by the Gaussian surface. Okay, so any doubts here up to this point? So I'll move further. Clear? So what is the discussion here? The discussion is that the flux lines will not pass through the top surface as well as the bottom surface because they are perpendicular to the direction of the flux density. Therefore, no fluxes cross through the top surface as well as the bottom surface. So eventually you'll be having only what? Flux passing through the curved surface only. Curved surface only. Okay. Yes. Next, come back to the next discussion. So we are not completed yet. So your total flux is equal to d into 2 pi into r into L. Okay. So this will be equal to what? Total charge enclosed. This is total charge enclosed. Okay. And total charge on the inner cylinder. So what is this total charge? That is nothing but the charge of the inner cylinder. The charge of the inner cylinder. So total charge on the inner cylinder. Okay, so that is nothing but um, using the surface charge density rho s into area, that is a volume, that is a volume, that is 2 pi r1 into L. That is a, you can call this one to rho s into 2 pi r1 into L. This happens to be uh, the surface area of the inner cylinder, and this is the surface charge density of the inner cylinder. Using this, you can find the total charge on the inner cylinder, which is equal to the flux crossing through the or this Gaussian surface. Okay, at this point. So this is nothing but the phi. This is nothing but q. So if you just equate and simplify, you will get it as E vector as rho L by 2 pi epsilon naught into R into AR cap. So you wonder why this rho L, how the rho L came. So I'll explain. Okay. Yes, this is the final equation. So you got two things over here: the flux and the charge. The flux, we got to know it as mm, d1 into 2 pi rl, that is d into 2 pi rl. Okay, and this we got to know it as rho s into 2 pi r1 into L. Okay, and d I can write in terms of electric field, that is epsilon naught into E into 2 pi r into L, rho s into 2 pi r1 into L. So this 2 pi and 2 pi gets cancelled, L and L gets cancelled. Okay, and you'll be getting epsilon naught into E into R is equal to rho s into R1. Rho s. So it got again closed down voluntarily. Yes, I have lost the file again. I'm sorry for that. Yes, we were discussing about the phi is equal to that this one. So it is d into 2 pi into r into L. Okay, and charge we got to know as rho s into 2 pi into r1 into L. This 2 pi and 2 pi gets cancelled, and this d into r into L is equal to rho s
Sir, LL
into
cap, sir.
L, yes, SL, yes, rho s into r1. So this L is cancelled here. So d I can write in terms of epsilon naught into E into R, rho s into R1. But rho s is nothing but total charge by area of the curved part. Area of the curved part. So total charge by 2 pi R1 into L. Okay. So it is. I'll continue the next one. One by, that is a total charge by 2 pi r1 into L, that is equal to 1 by 2 pi r1 into total charge by L. So it is 1 by 2 pi r1. So how do you write this one? Total charge by L.
Rho L.
Yes, it is nothing but dq by dl like this. It is nothing but 2 pi r1 into rho L. Okay, so this is exactly equal to what rho S. So if you substitute here, you will get the final expression like this. That is rho L by 2 pi epsilon into r into ar cap. The small mathematical simplification. This is on the Gaussian surface at the point which is between two cylinders. Yes. Next is we should continue the next class. So two things here. One is less than R1 and greater than R1, R2. So if it is clear for you, you can type 0 and on the chat box. Okay, I missed the files in between. I think if it is auto saved, I will get it back and I will share it to you. Okay. Yes. I'll stop at this point. I'll just let you know in the next class. Continuation of this one. Okay. And we shall solve problems after this one. So that completes the application of Gauss law.